Hi everyone, today at our seminar we have Slobodan Mitrović. Slobodan, please start.
Thank you. Thank you for the introduction and thank you for having me here. It's my great pleasure. Um, I will, do you see, just confirm that you see this in the full screen presentation mode?
So I don't think we see it in the full screen mode. We just see your PowerPoint window currently.
Okay, let me try to share this. Okay, sorry about this. Present now. This will work better.
Don't worry, I will edit this out.
Okay, how about now?
Yes, this works.
Yeah, that works.
Okay, perfect. Thank you. Yeah, so today's talk will be about random walks and how to generate them very efficiently in some distributed models of computation. And this is a joint work with Jakub Wolski, Krzysztof Onak, and Piotr Stankowski. So I guess this is the right audience, Polish people. Cool. So why do we care about random walks? Like one of the questions that one might ask. Well, they're building blocks for many algorithms. One of these really basic primitives in computer science, and they have a variety of applications. Like some of very industrial applications are, for instance, in web rating. Google built a company, started the company based on this kind of objects. There are then many applications in spectrograph theory, property testing, connectivity, and so on. And the basic question is how to compute random walks efficiently. And here we will be concerned with parallel models of computation. And so in addition, we will ask how to compute random walks in a small number of steps, parallel steps. So here is a very simple approach, right? I just want to emphasize that there is a way to very simple way to compute random walks, but it's not necessarily efficient. So say you want to compute a random walk of length 3 from vertex 3. So what you can do is, you select a random neighbor from V, then from this neighbor you select another random neighbor, you select one more random neighbor, and so on. And then that's it. That's an extremely simple approach, but the point is that this takes of L many rounds, where L is the length of walk that we want to construct. But ideally, we want to get something faster. And there are algorithms that give you faster than this many rounds. And I would say that maybe the central idea of all of these approaches is to try to predict where walk of certain length will end, so that you can prepare continuation of where certain prefix of walk that you want to compute ends. And just think of, you have an entire walk and you are trying to chop it into several smaller walks and then stitch it back together. And again, the central idea or the central challenge kind of is trying to predict where these stitches should happen. And this in some way asks you to predict the future, of these random walks that you still didn't generate. And this is also the main challenge. How on earth can we do this kind of thing? So the most actually of the presentation of the talk will be on answering this question: how we can predict the future in some sense. And before we go, let me just tell you, before even we look at any algorithm, let me just tell you what is known out there. So for instance, there is this result from 2012, which I believe was developed in the context of streaming, and anyhow, they use this idea of stitching, and they show how to generate length L random walks in essentially square root L many rounds, at least for undirected graphs. Right? And this is quite nice improvement. You get something which is quadratically faster than what we saw just a couple of slides ago. Right? And then they also study page rank. We will see later that page rank essentially can be reduced to computing many short random walks. And for page rank, the results that give you log n over epsilon random complexity. Just emphasize here that
can I ask a question?
Sure. Yes, of course.
So since we are already talking about rounds, what is the exact computation model, or more precisely, what is the communication model?
I see. Okay, so yes, sorry, I didn't discuss this. Let me first tell why I didn't. Because the idea that I will present, they are completely independent of any model of computation. But now, when we think how to implement this, one of the you can think of say MapReduce, Hadoop, NPC model of computation, where graph is partitioned across many machines. Each machine can hold n to the delta for some delta say less than 1, can hold n to the delta many edges or vertices, and then they can exchange messages between two rounds. After they perform computation, they can exchange messages. But the idea that I will present, sure.
So it's not like the communication graph is the input graph.
It is not. It is not. It is not.
Okay.
Yeah. Thanks. Yes. Yeah. Sorry for not being more specific about this. It is not. You can also think of TDAM. In fact, in the paper, we show also how to simulate this algorithm in TDAM. It would want to show that it works in semi-streaming model as well. But yes.
So these rounds for like if you take the algorithms from these papers and you try to implement them in MapReduce, then this is the number of rounds that you get, or
yes.
Okay. And what is epsilon here?
Okay, cool. This is interpretation probability, and I will show that in like 2 or 3 slides. I will define page rank, and then I will go back to this epsilon. This epsilon is interpretation probability for page rank.
Okay.
So these are the results which are known prior to our work. What essentially we get, if you look, if you have a look at this table below, I'm presenting this, I'm stating these bounds for MPC, for MapReduce, say, is essentially that you are getting exponential improvement. Right? And there is another very important feature that if you look at our result for page rank, this log of 1 over epsilon, 1 over epsilon is actually in log. And this is very important, and I will also get back to it very soon. Okay. Yeah. So these are the results, and here I emphasize that we are able to get multiple independent random walks. The reason why I'm saying this is that there is another work which appeared in 2011 that actually you can use to get one random walk, even in directed graphs in log L many rounds. But the point is that if you want to get multiple random walks by using this approach, they're dependent. And this is like very nice. The algorithm is elegant. But the point is that for many applications, you really would like to be able to obtain, say, polylog n random walks from each of the vertices in the graph. And page rank, in fact, is one of these applications. We also show in our work that another type of application is in property setting. And also in this case, really crucially rely on the fact that you are able to get multiple independent random walks. Right? So I'm just emphasizing this to make distinction between this result and also to credit this one that is able to give you, say, one single random walk from specific vertex. Okay, good. So here is the structure. Here is the structure, very high level structure of the rest of the talk. We will start with random walks in undirected graph. Then we will move to showing how to use this now kind of primitive that we will wait for undirected graphs to compute page rank. And then as a third part, we will actually see how to use page rank. If I give you a page rank algorithm as a primitive, how you can use it to get even directed random walks in general graphs. Good. So this is a very high level overview of the rest of the talk. Before I get to algorithms, let me just define a recall definition of page rank. So without looking even at this slide, page rank is actually a random walk where at every point with probability epsilon you jump to random vertex. Okay, and this is in this slide this red circle, right? That essentially says that again at every step you are making random walk, and at every step you're flipping a coin, and with probability epsilon you're saying I will now jump to a random vertex in the entire graph. And with probability 1 minus epsilon, you will continue just standard, like regular random walk, right? Nothing special. With probability 1 minus epsilon, nothing special happens. And this is what we call page rank. And 1 minus epsilon is called the damping factor, or epsilon is called also teleportation probability. And this is what epsilon means. And what you would like to output for page rank is station distribution. Would like to output pi for this matrix, walk matrix defined in this way. So this is page rank. Now, instead of going part 1, part 2, part 3, I would like to convince you that actually it's quite cool if you're able to compute page rank efficiently. That it almost immediately gives you a way to compute random walks in directed graphs. So let us see how. This is now the part 3. Think of it more as motivation for what's going to come next. So you want you're on input. You're given directed graph G, and you're given length L, which is the length of random walk that you want to compute. And what you would like to output is again walk of length L in G. Now what you will do simply is you will set epsilon. This epsilon again is teleportation probability. You will set epsilon to be something small, 1 over L, or even 1 over L times 1 over log n. So something small. And now you will compute a page rank walk in your graph GD and return this walk. And that's it. And actually you can show that with constant probability, this walk defined in the page rank walk will not have any random jump. But if it doesn't have any random jump, it is just a regular random walk, right? And since you're working with directed graphs, you will actually be able to output in this way a random walk in the directed graph. And here it was very crucial. Notice that epsilon is 1 over L. Usually we think of epsilon as being constant. But in this specific application, we are making epsilon being potentially much more than constant. Think of L as being at least polylog n, or even being n to the delta, like n to the 0.1. And so epsilon is really tiny. And so for this approach to be efficient, we actually needed to design some algorithm which would depend only logarithmically on 1 over epsilon. And then if you just look at the bounds that I showed you on second or third slide, you would, this is essentially how you get bound for directed random walks. Just plugging 1 over L instead of epsilon directly. And that's it. So again, once you have this second step, the second part, once you have page rank for directed random walks, then with just a bit more of work, you will be able to get directed.
Are you able to tell if in the generated page rank walk you jumped or not?
Yes, you would be able to. Yes, yes, yeah, a great question. So the algorithm itself, you will see more details in a moment, but the algorithm itself will follow this the definition, this page rank matrix, page rank walk matrix. It will follow this page rank walk matrix, and it will annotate each edge. It will annotate this edge whether it jumped or not. So
Okay.
you would be actually, when a jump happens, you would know that this actually was a jump, and in fact, these walks will be discarded in this application. But you know that if you repeat, if you run, say, log n walks instead of only one walk from each vertex, then one out of those log n with high probability actually wouldn't have any random jump, and that's it. And this is the walk you're having.
Okay, so you will generate multiple page rank walks, or not?
Yes. All of them in parallel, polylog n from each vertex.
Okay, thanks.
Thanks for the question. Oops. Okay. Good. So third part, easy peasy. Now let's go to the first part, which is again about generating random walks in undirected graphs. Okay. Good. So there is this idea that we mentioned on some of the first slides about stitching, right? You know, you want to compute a walk of random walk of length L from V. Well, there is an idea that you actually compute random walk of length L over 2 from each vertex, not only from V, but from each vertex. And now, say from V to W, you have a random walk of length L over 2. From W to X, you have random walk of length L over 2. So what would you do is you say, well, let me just merge these two walks together, right? And they would give me one random walk of length L from V, and I've just halved the number of steps that I have to perform. And that's cool. And now you can say, well, let us recurse, let us iterate this idea, and let us, you know, do this for length L over 2, then L over 4, and so on. Actually, we'll start from length like 1, 2, 4, 8, and so on. And that hopefully would give us log L iterations to compute this. The issue is that once you start, as you're going more into this process, as you're recursing, as you're making additional recursion, the thing is now getting more complicated. Now you have all of a sudden a bunch of vertices who would need, say, L over 4 walks of length L over 4. And you know, like someone from W would need length of L over 4, W would need from some other vertices, and so on. So the situation becomes very, very complex. And the reason is that W doesn't know a priori how many walks will pass through it and actually ask to stitch. Right. So this is now the challenge. And there is a way to resolve this, which is simply follow station distribution. Despite this is a station distribution, and here is what I mean. So instead of saying let me from V compute maybe one random walk of certain length, you will say that from V we will compute number of random walks which is proportional to pi of V, right? So say pi of V times n, but for every single vertex. And now the number of walks ending at the specific vertex will actually follow station distribution, right? We know that in expectation it will follow station distribution. And that's it. This now gives us a way to actually, in some sense, predict the future. So we know how many walks, how many prefixes of random walks will end at specific vertex, W say, and so we can pre-compute in advance this continuation from W for all of these walks. So this is the idea. And extremely nice feature of undirected graphs, right? G is undirected graphs. We are still working with undirected graphs. Is that pi of V is the compute. It is just degree of V divided by 2. Yeah, let me know if you have any questions on this. Okay. So what we can take away from this is that if we can follow pi, this allows us to predict the future. And actually, it is quite easy to compute pi in undirected graphs. And here, just a minor comment. It's very important, but just a minor that the number of walks you'll be performing at the end would actually depend on inversely proportionally to the minimum entry of pi. Because you want to execute from every vertex at least one walk, so you have to scale it up, right? And we know that in undirected graphs, we can scale it up by 2. This is what we get for undirected graphs. I mean, good. This idea was very successful for undirected graphs. Let's see why it wouldn't work for directed graphs. Well, so first of all, getting pi for directed graphs is difficult. I mean, difficult in the sense that compared to what you can do for undirected graphs, it's way more complicated, right? But now, even if someone comes and gives you pi on a silver plate, it's still the case that the smallest entry of pi for directed graphs can be super small. And now, if you recall what we said on the previous slide, that memory here will depend inversely proportional to the smallest entry. It means that this approach, even if you know pi, would require so much memory. It's not going to be. Okay. So we need some other ideas. Now this takes us to part 2, right? And we will compute page rank. We will instead of looking at directed walks, directed walks, we will look at page rank in indirected. Good. So this is again definition of page rank. And so here is what we said about random walks in directed graphs, that pi is difficult to compute, and even if you are able to compute pi, it would leave using the same stitching approach would require lots of memory. Now, for page rank, the situation is not much different. We still don't know how to compute pi of t. We still don't know how to compute page rank in a very simple way. But there is something now super nice that happens for page rank in directed graphs, like even in directed graphs, is that the smallest entry of this page rank vector, pi of v, is lower bounded by epsilon divided by n. And the idea is rather simple. It's because with probability epsilon, you will jump to around the vertex of the graph. So at every point, there is probability at least epsilon over n that a random walk will jump to specific vertex, graph, right? This immediately lowers bound entries of page rank. And again, this is awesome because now if we turn this into memory requirement that we shown a couple of slides ago, it means that we don't have any issues, that with n over epsilon much memory, additional n over epsilon much memory, we can actually implement this approach. The issue though is that we still don't know what is page rank, so we have to compute it. But once we know page rank, we can generate random walks. We can generate page rank random walks very efficiently. By the way, I will try to switch on my camera back. There was someone using video on the same internet, but if it starts, if you feel lost, if you don't hear me well, just let me know. I will turn off camera. Okay, good. So here is the question now is how to compute PageRank. And here is a result from 2002 that essentially tells you that PageRank, approximating PageRank, essentially boils down to computing n log n short random walks. And in fact, you need to compute roughly log n random walks from each vertex. Okay, so this is very nice. It means that now we can reduce the task of approximating PageRank to the task of computing lots of short random walks from each vertex simultaneously in the graph. Okay? This is also one of the applications that I mentioned early on, that there are certain applications where you want to compute many independent random walks. And this is also great news because remember that from what we saw for undirected graphs, it means that if you want to compute undirected PageRank, it's very simple. Right? We have all the tools in our hands. We know station distribution for undirected graphs. We will compute a small number of random walks, and then we will use these random walks to obtain PageRank. Okay, good. But the challenge is now again that the challenge is on directed random walks, on directed PageRank. And here is the first idea, and here is the first idea that we will use to get PageRank for directed graphs, which is to start from something that we know, and in this case it is PageRank for undirected graphs, and then to slightly inject directedness on the edges so that eventually we get PageRank for directed graphs. Okay? And let me now be more specific. So by G, U, I'm not sure whether you see my mouse. Can someone say whether you see my mouse or not?
Yes. Yes.
Okay, perfect. Thanks. So by G of U, on input, we will get, say, G of D, which is directed graph. But by G of U, I'll be denoting undirected version of this directed graph. You just ignore directions on the arcs, right, on the edges, and that's how you get G of U. Now, right, we are happy with G of U. We know how to compute PageRank for this guy, but we would like to get PageRank of G of D. And here is what we will define. We will define a sequence of graphs, Gj, which is defined as follows. With probability 1 minus j divided by log n, every edge, so for this, you will start simulating to obtain random walk in Gj for every edge independently. With probability 1 minus j divided by log n, you will follow undirected graph. And probability j divided by log n, you will follow directed graph. Right? And again, for one walk, you might have something like undirected, directed edge, undirected, directed, and so on. This process happens for each edge independently. And in particular, it means that G of 0 is just this undirected graph that you know. Awesome. And G of log n is something that we want to learn. Okay, good.
What is the range
of
J which you use?
Yes.
What is the range of J's which you use here? What are the values of J which you use here?
Oh, 0, 1, 2, they're integers from 0 through log n. We will start with. So we will start with GU, which is just G0, and then let me now show. We will start from GU. We said that you know how to compute PageRank from GU, and now we will sample a bunch of random walks, actually even slightly superlinear in n in total. I will sample n to the 1 plus little of 1 times log n many random walks. And now we will use these random walks in G0, and I will show you more details very soon. We'll use these random walks to get, we will transfer these random walks from G0 to G1. Okay, and now by using this result that you saw on the previous slide that says that page rank can be approximated by many short random walks, we will be able to approximate page rank for G1. Now we will do the same thing again. We will sample lots of random walks in G1, and then we will use these. We will transfer these random walks from G1 to G2 by rejection sampling, and then we will be able to use these random walks to estimate page rank in G2. And we will continue this way and eventually get to G GD directly. So this is, without going into details, this is what happens. That we are gradually injecting these steps. But let me now show you how to, you might be wondering, right, how we can even go from a walk in GJ to walk in GJ plus 1. So let me just show you now. So on input, assume that you have W, which is a walk in GJ. And what you would like to get is a walk in GJ plus 1 or to fail. So you're okay with failing occasionally. In fact, in the actual algorithm will fail relatively frequently, but it's okay. So you assume that you're okay to fail. So what you will do is you will perform rejection sampling on each edge of this walk W in GJ, so that you kind of adjust for different distribution of the edges. And here I'm even showing, it is actually a simple exercise, right? What one has to do. So simply, if you have an edge which is in W, and again W comes from GJ, then you know that with probability 1 minus J over log n, and this is just by definition, nothing else. We know that it comes from undirected graphs, but with the remaining probability it comes from directed graphs. And in order to use rejection sampling and change distribution of this walk to GJ plus 1, well, if it's sampled from directed graph, you can accept. But if it's sampled from undirected version, this probability to reject, otherwise you accept. And that's it. It's easy to verify that this will indeed, assuming that this walk W succeeds, conditioned on that, it is actually easy to verify that then the resulting walk will be will follow distribution of GJ plus 1. And you might wonder, right? We are rejecting sometimes. What is the probability of this rejection? It's very important. So let's discuss a bit more about this. So we said that an edge is rejected with probability 1 divided by J plus 1. So it means that the walk, entire walk that you get on input is accepted with probability 1 minus rejection probability to the length of this walk, and length of walk is log n over epsilon. Okay, and so you know if J is at least log n over 2, probability of acceptance is okay. This is why we need to sample n to the little of 1 many walks in parallel, so to assure that one of them will be accepted. But that's okay. It's a little of 1. But if J says 0, this approach doesn't work. And if you want intuitively, you know, you're starting with J0, which is only undirected graph. It has no information about the directed version of the graph. And how you can even expect that you can extract some directed edges from G0, because again, G0 corresponds entirely to undirected version of the input graph. And this is an issue if J is small. Okay, but there's something that we still learn. If J is large enough, and we can gradually improve, kind of boost the directedness of the edges. So this whole idea would work for J large enough. Okay, so let us now see how to handle this case J is equal to 0. Now, here is an attempt. Let us just pretend, random walk in undirected graph. It will select random walk from vertex 3. It will take one of the random edges around. And, what is probability that this random edge would be directed? Maybe the probability is okay, and if it's okay, if it's some constant, then we'll be also happy. Like recall that for G1, for graph G1, the mixture of these two graphs, you only have occasionally to hit directed edge. Most of the time, you will be following undirected graph. And it's not so unlikely maybe that you'll be able to hit directed edge, even just by taking the random name. So here is an illustration. Say that consider this vertex 3. These green edges are incoming, yellow edges are outgoing. So if you look at the undirected version of this graph, it sees 6 incident edges. It doesn't see these arrows, right? Good. So say I take a random edge incident to V, and what is the probability if that this edge is directed edge, outgoing directed edge? We like outgoing directed edge. What is the probability of that in this example? I mean, someone can say it's a very simple question, but just to make sure that we are on the same page.
I mean, 1 over log n, right?
I see you're thinking about this definition. If you ignore this definition completely, you're just taking a random edge from V, and you are simply asking whether this is directed or undirected edge with respect to GD. Like the probability is 1/2. You're happy if you take any of these.
Okay.
But you're right. You're right that if one in addition cares about this this 1 over log n, then that's what you get, right? But right in this example, even if you have no idea about anything else, you only see undirected graph, and you're saying, give me just random incident edge. It's 1/2 in this example. And this is good again for us, because with constant probability, this will be successful. And then as Shemek said, with probability 1 over 2 times log n, the whole process for one edge will be successful, right? 1 minus that probability, which is fairly high. Now this example is nice, but there are examples which are ugly in this regard, where you have so many incoming edges, but so few outgoing edges, so that if you take a random edge incident to V, very likely it will be incoming, but we would like to take outgoing edge. So this idea where we just kind of blindly take incident edges in undirected version of the graph and try to pretend that it will actually match, that will actually be directed edge, this may fail. This may fail in examples like this one. Okay. Good. And so what we can learn from this is that if our degree divided by degree is large, then we're happy, right? And if this is small, we don't like this. And here is the final idea.
Why is it okay to have a success probability even smaller than like a constant, like 1 over log n?
Success probability would be okay. So with as you said, with probability 1 over log n, we will actually want to hit yellow edge. With remaining probability, we are happy with either green or yellow edge. And now we are saying that in addition, with probability like in case we want to in case we need to hit directed edge, we want that the probability of success in that case, which is already conditioning on some event that happens with probability 1 over log log n, we don't want this to be too small. So you see the probability success is actually in this case is more than 1 over log log n. It is only in this. It is only in these events that we hit with probability 1 over log log n that we want success to be high. But otherwise, it is already. Otherwise, we don't care whether we hit yellow or green edge. Does it make sense?
Yes.
Okay, we can. I don't know whether you said it doesn't or it doesn't, but okay, I will just continue. But we can go. We can go back to this. So this also, let me just interpret this differently. It means that on average, something like log n divided by log n, log n divided by log n edges would be such that you actually have to make them directed. The remaining edges can be undirected. But now if you take 1/2 to log n divided by log n times some constant, that you will get actually this answer to the little of 1.
Okay, that makes sense.
Okay, thanks. Okay, so we said that this case on the right is ugly. So what we will do, well, we will simply transform the graph so that we avoid this. Okay, so what does it mean? So here is our vertex that has n incoming edges. We will not, and this vertex right on the left, it has one outgoing edge. Well, we will not immediately point all these incoming edges to V, but instead we will create a layer of vertices, and this thick edge just refers to n over 2 parallel edges between this V log n and V log n minus 1. So all these edges, green edges that you see on the left, will be the same green edges that go into V log n. Now from V log n to V log n minus 1, we will have the number of edges that go in, then n over 4 edges and so on. And then if we inject, instead of V, if we inject a path of length log n, where again you have lots of parallel edges in between, if we inject this path, it will allow us, it will enable us to have this nice ratio of outgoing and total degree, right? And once we have this nice ratio, then actually we can run this idea that we had before. Because now if you look at V log n and you're saying give me a random edge, if you disregard directions, with probability 1 over 3, this random edge would be actually outgoing edge. Would be one of these parallel edges. And we said that we like this. Now the graph is slightly different. Now the graph is different. One has to account for that when computing when computing these random walks. They now have to be a bit longer because each vertex turns into a path of length log n, and your epsilon has to go down and so on. So there are some things to be done, but this is the main idea, that you transform a graph and then avoid this next example and get everything going. And that's it. So that's the approach for directed page rank. So again, just to reiterate this, that if you know pi, if you know station distribution, then it can help you really a lot. And one of the applications that we saw is how to estimate page rank. Okay? Then we saw this idea where we actually start from, we would like to get page rank for directed graphs, which is hard to get just directly. But what we instead saw is how to start with undirected graphs and then gradually add more and more of the directed version of the graph, unless we finally converge to directed graphs. Then we saw also a couple of ideas how to make this, right? Rejection sampling and then transforming these graphs so that you get something. And I said that for this, once you transform a graph, you need to work with epsilon, which becomes all of a sudden much smaller. But you might wonder whether we have to pay for this, and the answer is yes. But then similar ideas, I will just skip over this. But then actually using the similar ideas, you can start with epsilon. Which is say 1/2, and then gradually you can reduce this epsilon to be something small, while paying only log of 1/epsilon of this number of reductions or transitions that you're making. Right. But I will not go over this. Just as that one indeed has to pay something for wanting to make this epsilon small. And before I go to my last slide, let me just looking back, you might be wondering what was now so special about page rank, right? That we saw this slide at some point, and we said that just by looking at pi, at station distribution of directed random walks, it seems to be very hard to extract something efficient. But we are still playing with, we are still working with station distributions. Just now of page rank, and now all of a sudden we can actually extract directed random walks. And you might wonder, why is it the case? So here is my intuition is that page rank, somehow the way we define it, it gives you this station distribution which is valid up to walks of certain length. Beyond length L, this result that is the algorithm that we described will not work, right? But if you look at station distribution for directed graphs, it gives you this kind of perfect precision. It tells you that this station distribution is valid even if you want to compute walks of length 2 to the L. It's super far in the future, but we don't need that. And then page rank then can be seen as adding enough maybe noise or relaxation to this station distribution so that you still capture the object that you like, but you don't need to capture much more beyond what you need. And that's it. I would conclude with this, and thanks a lot. Well, let me know if you have any questions or anything was unclear. Here is one just open question, which I think is probably the most interesting in here is to get rid of these dependence in the memory. And again, this dependence is coming from our rejection probability. If you remember, I show you that we will accept walk with probability and to the minus little of 1, meaning that we have to sample many of them in parallel, and this little of 1 is what we have to pay. And getting polylog n instead of little of 1, I think is a very interesting open question and also would have implications. Thank you.
Thanks. That was really nice.
Thank you.
So, of course, I invite members of the audience to ask the questions.
Maybe before someone comes up with questions. So again, just getting back to what you asked, why it is okay that the success probability is 1/2. And like again, because just to get to that event, we already have to be sort of unlucky, which happens with probability 1/log n. So the success, the failure probability in total would be 1/2 times 1/log n. So that would be failure probability, and everything else would be success probability, which is now, it's not 1, but it's very close to 1.
As far as I understand, on a single step you can sample more random walks, and you just accept that only a small fraction of them will be successful, because this small fraction is n to the minus small of 1.
Yes, exactly. Yes.
So I also want to be sure, because you are approximating PageRank, but it's not hurting us. It's not leaking into the approximation of the random walks, because we are only doing it to allocate enough sampled random walks from vertices, right?
Yes, you're right. It's a very good question. What I cheated a bit. What I showed in the first part, it was assuming that you know perfect station distribution, but one can show that even if you have approximation, 1 plus epsilon approximate, where epsilon is constant, that then still you can use this teaching idea. Now you have to be slightly more careful, but it's possible. It's somewhat messier, but you're right. That's a very good question. Yes. Yeah, because if you have a good approximation intuitively, it just means that you will sort of be able to predict what happens, not always very precisely, but you will prepare for a bit more work, wanting continuation from every vertex, and then you will just discard what is left over, and that's how you proceed.
One question, I think I missed something when you were talking about PageRank of undirected graphs. Correct me if I'm wrong, but this is something like almost trivial. Like we can we can get the PageRank of an undirected graph just looking at the degree of the vertex.
Oh, that.
Or not.
So when you said trivial, I mean the following: you compute walks of length log n over epsilon. You would introduce jumps, and when the walk jumps, you cut at that point. Then to get a PageRank, you're looking at how many walks end at a specific vertex, and you divide by the total number of walks. So this is how you can get approximate PageRank. But to get
in undirected graphs, wouldn't PageRank be just weighted average between uniform distribution and the stationary distribution?
No. I think one can come up with examples where it's not the case. I see what you mean. You want to decouple these two things. It's not the case.
Okay.
But the question makes a lot of sense. I mean, we looked at such examples and tried to break this approach ourselves. So I think the question makes a lot of sense, but it's not the case. Yeah, it's more complicated than that, the whole process. Because once you get around the vertex, then again something depends to what kind of region of you get to, how quickly you will leave this region, and then it is just kind of first order approximation what you're saying. But a great point.
If there are no more questions, I will stop the recording.